In this video, we're going to talk about degrees and radians. In the past, when we work with angles, we always use degrees. So from here to here, the angle from here to here is 90 degrees. The angle from here to here would be 180 degrees, and one revolution here would give us 360 degrees. And when we were working with trigonometry, if you get 3 here, you get 3 divided by 7, and then you inverse tan, it will give you 23 degrees. Well, an alternative to using degrees is to use radians. So from here to here, it would give you 180 degrees. Well, with radians, from here to here, it would be pi. And why pi? There's a reason why pi later on. Hopefully you will be able to see why later on. And from here all the way around here, it would, well, normally it would be 360 60 degrees. Well, one revolution here would be 2 pi. And why 2 pi? Hopefully later on you will understand why. The reason is by making it 2 pi, it really simplifies things. Well, from here to here, normally it's 160. It will normally be 180 degrees. Well, in radians, from here to here, it is it is pi, but it's roughly 3.141. So you can imagine this as being roughly, well, from here to here, it's 3.141. You can imagine it as having 3 pieces. So, for example, from here, cut it into roughly 3 equal pieces. So here, so you can think of this as being 1 radian. So this is 1 radian, and then this here is another radian, and this here is roughly another radian. So from here to here, it is pi. Okay, but inside your mind, think of it as being roughly 3 segments, 3 equal segments, and this here is like 1 radian. Okay, okay, so 1 revolution here, it is 2 pi, and from here to here, it is just pi. And here's the reason why we use pi here. When you're trying to understand things moving in a circular motion, so for example, the sun here, and this here is the Earth orbiting the sun. I know the Earth doesn't orbit the sun perfectly, but we can use it to roughly understand what's going on. Or we can imagine the center as being the Earth, and this here is a satellite. So the satellite starts here, and then it orbits the Earth. Okay. Let's just imagine it at the moment it's the Earth and a satellite. Let's say the satellite is here, and then this here is the center of the Earth. This here is a satellite. The distance here, let's just call it r. Let's just say the satellite starts here, and then it sweeps an angle of 37 degrees. Let's just say it makes it sweeps an angle of 37 degrees. Now the question is, what is this distance here? What is the distance traveled by the satellite, which is the distance from here to here? Now normally, when you work in degrees, you would normally do this. You would work out the whole distance here, which is the circumference of the circle. So you would do this: 2 pi r, which would give you, remember the distance from the center of the Earth to the satellite is r. Okay, we're just pretending. So 2 pi r would give us the whole distance here, and then you would then cut it into 360 equal pieces. So basically you would work out the whole distance here, and then you would cut up into 360 equal pieces, blah blah blah. And then because you've made an angle of 37 degrees, you in effect would need 37 of these little pieces. So you would then times 37. Okay, so okay, let's just say now we're not going to say 37, we're going to say theta. The satellite has just made an angle of theta. Okay, so what is the question is, what is the distance covered by the satellite? So you would normally do this. Work out the circumference of the circle, 2 pi r, and then cut it up into 360 equal pieces, and then you would times the number, well, times the angle that has been swept through. So you would times theta. So this whole expression here would represent the distance here. You would then tidy this up, so this would become 2 pi r theta over 360, and then maybe again you would tidy up to pi r theta 180. Okay. Now working in radians is much better, and here's why. From here to here, it's well, you would work out the circumference, which is 2 pi r. That would give you the whole circumference, and then divided by the whole thing here, which is 2 pi, divided by the whole thing there, which is 2 pi, and then you would get whatever this theta is. You would then times this theta. You would then times theta. Okay, so this whole expression here represents this distance traveled here, and then tidy up here. So it would be like this, because the theta then gets multiplied to the top. And look, these two would kill off each other, giving you this. So this thing here represents a distance traveled by the satellite. If you work in degrees, this here would represent the distance. You can see here, we don't really, the pi complicates things later on. And this number here is, well, it's quite ugly. You've got this pi and this 180. Whereas if you work in radians, this here would represent the distance traveled. Okay, or another one would be this. Suppose you have a planet here orbiting a star here, a sun. What is the, let's say it starts here and then it sweeps through this angle here. What is the area of this thing here? Well, if you work in degrees, you would do this. Work out the area of the whole circle. So you would do this: pi r squared, and then cut out into 360 equal pieces. So what you're doing is you're cutting it up into 360 equal pieces here. Okay, so this here would represent one piece here, and because you swept through an angle of theta, you would then times theta. So for example, hang on, let's start again. Pi, well, the satellite, well, the planet is here, the sun is here. It has just swept through an angle of theta. You want to know the area of this whole thing here. You would normally do this: pi r squared, cut out into 360 equal pieces, and then times this many pieces, which is theta. So this here would represent the area. So you would then tidy up, making it look like this. Hang on, 360. You see, this here represents the area here, the area that's been swept through. If you work in radians, it would be this. Work out the area of the whole circle, work out the area of the whole circle, which is pi r squared, and then split it through one whole revolution, which is 2 pi here, and then get this many pieces here, if you like. So you would times it by theta, and then again it gets multiplied to the top, so it will be this, and then divided by 2 pi, and then the 2 pi's here would cancel each other out, so it would give you this over 2. You see, working in degrees, this area here would be this. Working radians is just simply this. Look at this. You don't need the pi. This here is, well, the 2 here is slightly neater than the 360. But the important thing is that if you work in degrees, you're going to get pi carried all the way through whatever. Well, you don't need the pi. well, you can see that this here is much neater. Okay, and when you look at the graph, degrees, when you work in degrees, your sine graph will look like this: 180, 360. So this is one revolution, and then, well, this is your normal sine graph when you work in degrees. Well, working in radians, it would be pi, 2 pi, 3 pi, negative pi, and it would look like this. The whole point of this thing, the whole point of radians, is that it really simplifies things. When you want to work out this distance here, it's much simpler working radians. When you want to know this area here, it's much easier to work in radians. And in the future, we will need to try to understand things that are moving in a circular motion. That's why it's better to work in radians. From now on, we're going to work in radians. Okay.